Alright, so today I'm doing a proof of Pick's theorem for everybody. It's a proof first part out by George Pick, an Austrian mathematician in 1899. And what it is when you have an n-sided polygon with the vertexes on the lattice points of the graph, you have a formula for the area that is equal to I plus b over 2 minus 1, where I are the lattice points inside the polygon, b are the lattice points on the edge of the polygon, and then divided by 2, which we'll get to later. And to get to that, the first thing we need to do is prove that the Euler characteristic of any simple planar graph is equal to 2, which we briefly talked about in class, where v minus e plus f is equal to 2. And to prove that, I'm going to be doing induction on the vertices. So when we do that with the induction, the base case will be v is equal to 1. And when v is equal to 1, you have two cases. For case 1, we have where it's just a point in space and nothing around it, so there's no edges. So there'll be 1 v, 0 edges, and 1 face for the graph all around it, and that'll be equal to 2. And then for case 2, we have where there is a vertex, but this time it's part of it's the beginning and end of a Jordan curve, which is a simple loop. And then you can have as many loops beginning and ending at the point because they're not intersecting with each other at any point. So what we have there is that the v is equal to 1, and then you'll notice that with each edge we add, we also are adding a new face. So that means that with one edge, so with e equals 1, we would have f equal e plus 1. So for any edge e, we have e plus 1 faces. So when v is equal to 1, we have 1, then the e's will cancel out, and we get 1 plus 1 is equal to 2. So we have proved that the base case holds for the vertices. That's not the right word. And after the base case holds, we can do the inductive step, and we can show that we're going to assume that n minus e plus f is equal to 2 for some n greater than or equal to 1. And then when we have an n plus 1 vertice graph, we can take two vertices connected by an edge, we contract them together, and then we get an n vertice graph. And from here, we're assuming that an n vertice graph fits this, assuming that it has an Euler characteristic of 2, which would imply that an n plus 1 minus an e plus 1 plus f graph is also has an Euler characteristic of 2. And we get that from when we contract an n plus 1 vertice graph when they're connected by an edge. We contract those two vertices, we're also eliminating an edge. Think of like a square where you contract two vertices together, then you get a right triangle. And how we've eliminated we eliminate one vertex and eliminated one edge, which gives us that. So when we add that vertex and that edge back in, we get this equation, which would show that this would still be a vertex of 2. An Euler characteristic of 2. And then this proves that all planar graphs would have an Euler characteristic of 2, which is the first part we need for the proof of the Pick's theorem. Okay, so after proving that the Euler characteristic of each planar graph is equal to 2, we can now move on to the formal proof for Pick's theorem, which will come in 3 parts. The first part being proving that the area of all small triangles, or primitive triangles, is equal to 1/2. And then we'll be triangulating the polygon, which means putting as many small triangles in this polygon as we can. And we're determining the number of small triangles that we have now put into that polygon. And for the area of a small triangle, first we'll talk about what a small triangle is. It's just any triangle where the vertexes are the only 3 lattice points in the triangle. So if there's no lattice points inside the triangle, there's none on the boundary of the triangle. Think of like a right triangle that starts here, here, and here. And then for the area of that triangle, for right triangle, it's pretty intuitive. It's 1/2 already because the base times height are both 1, and then divided by 2. But for a triangle like this, it's a little less obvious that the area will be 1/2, but it still is 1/2. And then one important aspect of this triangle is that the point MN is visible from the point 0, 0. And what that just means is that there are no lattice points on that boundary line, and there's no lattice points inside the triangle as well. And then since one property of the Mn being visible means that they are coprime. And then because M and N are coprime, we have that there exists integers P and Q such that P times M plus Q times N is equal to 1. And now with the knowledge that these points are, that M and N are coprime with each other, we can move on to finding the area of a small triangle. And to do this, we will in fact be expanding the small triangle into a small parallelogram. And to do that, we will treat the line from 0, 0, the RS, as a vector, and the segment from 0, 0 to MN as a vector as well. And we're going to add those vectors together. And when we do that, we will get the point over here. That will be the point M plus R, N plus S. And with that, we'll come back down here. All 4 points will be visible. We'll come back here and use this, and we'll have the vertex. We'll have the matrix of PQ minus NM. And then we'll have that the determinant of PQ minus NM is equal to PM minus Q times negative N, which is the same thing as PM plus QN. And with that, we have that equal to 1. So with this right here, the PQ minus NM matrix, what that is that would be a transform matrix. And since the transform matrix has a determinant of 1, that means any transformation we use with this matrix will not change the area of the parallelogram that we have up here. Alright, so we have the transform matrix here of PQ minus N and M. And then we can go ahead and multiply that by this point here, Mn, which will give us the transform point of the Mn point. So we'll have Pm plus Qn, then we will have negative Nm plus Mn. And we have that Pm plus Qn is equal to 1, so we have that as 1. And then we have negative Nm plus Mn, which is the same thing, and adding in positive to negative itself is 0. So we have that the new point of Mn becomes 1, 0. Alright, and so now we have that the point of the Mn transform is at 1, 0, or one space to the right of the origin. Then for the RS point and the M plus R, N plus S point, we have the transforms coming out to these two points right here. And you'll see that the y coordinates of both of them are the same, and they have to be non-zero, so they were 0. They'd be on the same line as the other 2 points, and we have no area whatsoever. And then notice that the x coordinates are almost the same, except they're separated by 1. And then so this is I drew it's just a quick example of what a parallelogram could look like. It might not be this, and we'll say that, and then we'll go ahead and prove that the area is equal to 1 by contradiction. Or but the height is also equal to 1, which will lead to the area being 1. So we're going to, for the contradiction, we're going to assume that the height is greater than 1. And for that, since I drew it as the height is equal to 1, so for the height to be greater than 1, this point would extend out to here. This one would extend out to here. And as you can see, since this is this came from 2 primitive small triangles, but we see now that this can no longer be a primitive parallelogram because there are now lattice points that are on the boundary. When for it to be a primitive parallelogram, there can be no lattice points on the boundary. Lattice points can only be at the vertex. So we see by contradiction that the height cannot be greater than 1 because it no longer becomes a primitive parallelogram. And if the height was less than 1, it also can't be a primitive parallelogram because then we'd have maybe a point right here and right here, and those points are not part of the lattice, so there are now vertexes not on the lattice, so that can no longer be a primitive parallelogram either. So we proved by contradiction that the area of a primitive parallelogram, the height of a primitive parallelogram is also equal to 1, and so is the base, and the area of a parallelogram is the base times the height. So we've proven that the area of a primitive parallelogram is equal to 1, and then we can extend that to a triangle, because if we drop that right there, we now get rid of those little dots right there. we now have two triangles, both with three lattice points, all at the vertex, which divides the parallelogram in half. So based on the parallelogram having area of 1, we now have two equal triangles that are also primitive triangles, and we can show that, and we know that the area of a triangle is half the area of the parallelogram by doing it up here as well. And so we have the area of a primitive triangle, of all primitive triangles, is equal to 1/2. Alright, and so after proving that the area of all small triangles is equal to 1/2, what we do next is we will triangularize our polygon into as many small triangles as we can fit in there. I've already done some of them are intuitive ones in the middle, making all the right triangles, but you'll see some of these at the bottom can be a little trickier to do. So what you could do is you just pick a vertex like right here, and we'll see it has the one right there, but it also can go to this vertex right here. So we have a new triangle there. Then it also goes to this vertex here, making a new triangle there. Then it also goes to this vertex out here, making two more triangles. And we have this one right here. This one's a little simpler to see than that one. It just goes up to this triangle right, up to that vertex point right there, and we make two new triangles. All of these triangles we're making are simple triangles because they only have vertex points on the edges. Only lattice points in the triangles are the vertexes. Then we have a couple more to make right over here. Bring that one to there, then bring it down to there, and yeah, don't need to bring it down to there because that would just be the line already there. And so after triangulating the polygon, we have all these individual, small, simple, primitive triangles, all with an area of 1/2. And the next step will be to determine the number of small triangles that are in the polygon. And you may have noticed that while we were dividing all these lines, making new triangles, that we were also adding a new face every time we did it. So there are now as many number of faces of triangles in here, or a number of faces inside the polygon. So a total number of faces. The number of triangles actually. So the number of triangles will be equal to the number of faces minus 1. And then having this number of triangles is equal to the number of faces minus 1, we can now go onto the edges, and we will have 3 times f minus 1, which is 3 times the number of triangles. We'll multiply by 3 because each triangle has 3 sides. And then we have the boundary edges, and then for the triangles, the interior edges are all counted twice. Then the outside edge will be counted once, and then that'll come out to 2e right there. And what we can do next is we can go ahead and distribute the 3 through, and we will have 3f minus 3, and we can go ahead and move the e boundary to the other side. And then the next step will be to solve for f, and we could divide by 3, but an easy way to do it would just be to subtract 2f from each side. So we will have f is equal to 2e. We'll go ahead and write the 2f right there for now, subtracted by the e boundaries, plus 3. And what this becomes is we can factor the 2 out of here, so that becomes 2 times e minus f minus the e boundary plus 3. Now calling back to the Euler characteristic formula, where we have for planar graphs, where we have v minus e plus f is equal to 2. That can be written as e minus f is equal to v minus 2. And then we have the e minus f right there, so we have that f is equal to 2 times v minus 2 minus the e boundary plus the 3. And then we have for the vertexes are all the vertexes on the edge of the graph and inside of the polygon. And we also have that based on the formula up here that I mentioned at the beginning, that I are all the number of vertexes on the inside of the polygon, and B are the boundary vertex on the polygon. So we have that V is equal to I plus B, and then we also have that the E boundary is equal to the number of vertexes on the bound is equal to that the E boundary will also be equal to B, as each edge between each vertex is a new edge. So every edge on the boundary leads to E bound total also being B. So we will have f is equal to 2 times I plus b minus 2 minus b plus 3. And then the next step will be to go ahead and distribute the 2 through, and we'll get 2i plus 2b minus 4, don't need that parenthesis, minus b plus 3. And then with that, f would become 2i, then we have 2b minus b, so we have 2i plus b, then minus 4 plus 3 is minus 1. So we have the formula for the number of faces that are here, which is helpful, but then we're going to go ahead and get to we want the number of triangles, because each triangle has an area of 1/2. So we're going to go ahead and subtract both sides by 1 to get that. So we have f minus 1 equals 2i plus b minus 2. And now we have the formula for the number of triangles, then the area of each triangle, and so the area will be the number of triangles, and the area of the triangle. So we'll go ahead and divide through by 2. And then we have that the area of the polygon will be equal to I plus b over 2 minus 1. And so the area of this polygon will be the number of interior vertex plus the boundary vertex divided by 2 minus 1. And if we were to count that real quick, for this polygon right here, we have I is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And b would be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we'd have the area is equal to 14 plus 16 over 2 minus 1, which would be 22 minus 1, or 21. And so here is where the proof stops, and we have proved that for Pick's theorem, the area of any n-sided polygon is equal to the number of interior lattice points plus the boundary lattice points divided by 2 minus 1.